The global maritime industry faces an impossibly expensive deadline. To replace aging fleets, companies must rapidly design and build zero-carbon ships equipped for deep-sea hydrogen and ammonia fuels. This line chart visualizes the financial hurdle, a sharp hockey stick spike in the capital expenditure required over the next decade. Funding this transition means paying for novel engine designs, specialized fuel containment systems, and entirely new port infrastructure. Simultaneously, an older generation of vessels is reaching the end of its operational lifespan. Experts forecast a 5-fold increase in retiring ships globally within the next 10 years. Shipping companies are caught between these two realities. They have to pay for the most expensive modernization effort in maritime history, right at the exact moment they must dispose of an enormous obsolete fleet. For decades, the final destination for these retiring giants has been muddy tidal beaches. They were viewed as chaotic environmental problems and massive financial liabilities. Economically, these decommissioned hulls function as massive floating material banks. Beneath the weathered paint, between 85 and 95% of a vessel's mass is high-grade steel. Across the global fleet, over 100 million tons of premium steel sit locked inside these aging hulls, waiting to be reclaimed. Extracting this dormant physical capital now offers the industry its most significant source of strategic leverage. A decaying hull scattered across a beach has almost zero strategic value. To turn that raw scrap into liquid capital, the industry relies on reverse logistics, a highly organized system designed to retrieve, sort, and certify materials so they can re-enter the supply chain. As we see in this 3D animation, the modern dismantling process separates a ship into clearly defined, certified components. Facilities use digital material passports and rigorous hazard inventories to meticulously track and audit every individual steel plate. Advanced recycling yards deploy AI-driven planning tools and robotic automation to execute precise cuts. They optimize the exact sequence of material removal to ensure both worker safety and maximum yield. This precision sorting prevents premium maritime steel from being downgraded or lost inside a tabled pile of low-value scrap. By applying strict reverse logistics, a liability at the end of its life becomes a highly traceable premium secondary raw material ready for immediate resale. This organized scrap enters a global raw materials market currently defined by extreme volatility and unpredictable supply shocks. Global steelmakers are aggressively moving away from coal-heavy blast furnaces. They are adopting electric arc furnaces, a technology that melts existing metal and requires a massive, steady supply of clean, high-quality scrap to function. This bar chart directly compares the environmental footprint of both methods. Recycling maritime steel completely bypasses virgin iron ore extraction, saving roughly 1.5 to 1.6 tons of carbon dioxide emissions for every single ton of steel recovered. Securing a domestic, circular supply of this recovered steel gives both the maritime and construction sectors crucial resilience. When global virgin material supply chains break down, these industries have an immediate buffer. Through calculated recovery methods, the maritime sector now produces the exact low-carbon industrial asset that heavy manufacturing desperately needs. We can now trace the value of that recovered steel back to the original problem, the staggering cost of building the new zero-carbon shipping fleet. Selling scrap steel won't pay for a new hydrogen ship entirely, but maximizing material recovery drives down costs. Integrating recycled steel also lowers Scope 3 embodied emissions, the footprint from manufacturing the ship's components. Providing verified circular recycling metrics improves a shipping company's ESG profile, strengthens their balance sheet, and makes clean energy fleet projects far more bankable to investors. The capital recouped from responsible, high-yield dismantling provides the economic leverage needed to offset the heavy upfront expenses of modernization. The long-term strategy for maritime trade requires abandoning the linear model of extract, build, burn, and abandon. Instead, fleets operate on a self-reinforcing cycle. New vessel construction is intrinsically linked to resource recovery from the previous generation, reducing demand for virgin materials. Navigating the brutal economics of deep decarbonization takes immense capital. The industry cannot afford to start from scratch every time a vessel ages out. The zero-emission pioneers of tomorrow are being strategically funded and physically built from the extracted wealth of the fleets of the past.